Magnets. They're everywhere, on our fridges, inside our computers. They literally make the world spin. We use them constantly, but how do they actually work? How does one thing pull another thing from across the room without even touching it? It feels like magic. Well, today, we're going to pull back the curtain and demystify this incredible invisible force.
So here's the game plan. We're going to start with the basics. What's the difference between a magnet and just a paperclip? Then we'll cover the one unbreakable rule that all magnets live by. After that, we'll make the invisible visible by looking at magnetic fields. We'll even do a little power ranking of different magnets, and then we'll put it all together.
All right, first things first, we have to get one really important distinction straight. Honestly, this is the foundation for understanding everything else about magnets, and it all boils down to one word: alignment. I mean, think about it. They clearly interact, right? The magnet sticks to the paperclip. But one of them is doing all the work, and the other is just kind of going along for the ride. So what is really going on there?
Okay, so here's the deal. A magnet, a real magnet, is special because it creates its own magnetic field all the time. Inside, it's packed with what you can think of as tiny atomic magnets, or domains, and they're all lined up, all pointing in the same direction. Now, a magnetic material like a paperclip has those same little domains, but they're a total mess, all jumbled up and pointing in random directions. They don't have their own field, they just react when a real magnet comes near.
And this is where my favorite analogy comes in. It's perfect. A magnet is like a perfectly synchronized marching band. Everyone is in step, facing the same way, creating this one big, powerful, unified movement. A magnetic material, though, that's just a disorganized crowd of people milling around. They only start to line up and move together when the marching band passes by and gets their attention.
Okay, so now we know what makes a magnet a magnet. Let's dig into the fundamental rules they all have to follow. I don't care if it's a tiny little magnet holding up a drawing or a massive one in a lab. They all play by the exact same laws, and it is all about their poles.
This is the one you probably remember from science class. It's so simple, and it is absolutely unbreakable. Every magnet has a north and a south pole. You put a north near a south, they pull together. You try to push two norths or two souths together, they push each other apart. Every single time.
So this simple rule leads to a really fascinating, kind of weird property. You take a normal bar magnet, right? It's got a north pole on one end, a south pole on the other. A perfect little duo.
But what do you think happens if you snap it in the middle? Do you get a lonely north pole over here and a lonely south pole over there? Nope, no way. You get two brand new, smaller, but totally complete magnets, each with its very own north and south pole. You can't isolate one pole. They always come in pairs.
Okay, we know that magnets attract and repel. But how? How do they do it from a distance? The answer lies in this invisible architecture, this force field that surrounds every single magnet.
This is what we call the magnetic field. It's the whole reason magnets have that action at a distance power. You can think of it like a magnet's personal bubble of influence. Anything magnetic that wanders into this bubble is going to feel that force, whether it's through paper, wood, or just thin air.
Now, we can't see this field, but we can map it out using something called field lines. And the rule is they always flow out from the North Pole and they loop all the way around to enter the South Pole. And here's the really cool part. Wherever those lines are packed together the tightest, that's where the force is strongest, which of course is right at the poles themselves.
But this is the big question, isn't it? It's one thing to draw some lines on a piece of paper, but how did those imaginary lines create a real physical pull that you can actually feel in your hands?
It's because those field lines act like invisible, stretched rubber bands. Seriously. When a north and a south pole get close, their fields reach out and link up, creating a direct path. And just like rubber bands, those lines want to snap back and become as short as possible. That contracting, that shortening, that is the physical pull we feel as attraction.
So now we know the mechanics, but anyone who's ever played with magnets knows that some are, well, kind of wimpy, while others are scarily strong. Not all magnets are created equal, so let's talk about power. Okay, so here are the main players. You've got your basic ceramic magnets. Those are the classic black ones on your fridge. Then you have Alnico magnets, which are a bit stronger and handle heat better. But then you have the heavy hitters, neodymium magnets. These things are made from rare earth metals and they are shockingly powerful for their size. And then, in a class of their own, you have electromagnets, which you can turn on and off with electricity.
And wow, this chart really puts it all into perspective. Your standard ceramic magnet is a featherweight.
Alnico is definitely stronger, but just look at neodymium. It is in a completely different universe. These are, without a doubt, the heavyweight champions of the permanent magnet world.
So what's their secret? Well, it boils down to three main things. First, the material itself. Neodymium is just naturally amazing at keeping all its little atomic domains in that perfect alignment. Second is just size. Generally, a bigger magnet is a stronger magnet. And third is temperature. Get a magnet too hot, and all that heat energy can literally shake those perfectly aligned domains back into a disorganized, jumbled mess, completely ruining it.
All right, let's tie all of this together. We've gone from a simple paperclip all the way up to the most powerful magnets on Earth. Let's create one final clear picture. When you boil it all down, it's actually this simple. A magnet is just a special material where trillions upon trillions of tiny atomic domains have stopped being a chaotic crowd and have all lined up to point in the exact same direction. And that perfect unified alignment is what generates the powerful, invisible force field that can reach out and shape the world around it. So, if you remember just one thing from all of this, let it be the marching band. The incredible power of magnetism isn't some strange magic, it's just the power of perfect, synchronized alignment on a massive scale.
And that leaves us with a final thought to chew on. We've seen that this amazing force is really just a product of getting things to line up. It really makes you wonder, what other powerful forces, in technology, in nature, or maybe even in our own lives, are just waiting to be unleashed, if only we could get everything to point in the same direction?